All right, so hey guys, I'll be going over some stuff about some elementary quantum basics. I'll just pause and let me know if you guys have any questions. But yeah, very excited. So, firstly, I just wanted to go over some of the math that we learned in quantum computing, specifically Dirac notation, which is a way of kind of simplifying qubit vectors um, into this notation that makes it a little bit easier to work with. And so when you have a vector, like one-dimensional vector, kind of like these vectors are represented as qubits via Dirac notation, which is when you have, it is the line with a number with numbers in between it and then a caret symbol. And if you square the amount of numbers inside of the notation, that is how big your one-dimensional vector is, and that represents how many states are representable based on how many qubits you have. So if you look at the -10 caret Dirac notation, you can see that that is a vector with 4 states because there's 2 qubits inside of the notation. And the way the math works is it's 2 to the nth based on how many qubits that you have. So if there were 3 numbers in between there, then you would have 8 possible states for qubit 16 and on and on and on. And as you can see, it's based on positioning of the numbers. If you have, for instance, if it's 1 1 in the Dirac notation, then you're representing the state in the 4th slot. If you have 1 0, then it's the 3rd slot. If you have 0 1, 2nd slot, it's 0 0, 1st slot. So that represents the 4 possible states. And sorry. And then so these notations, when you branch it out into vectors, these can represent the probability density matrix if you square all the values inside of the vector once you multiply it out. And if you have, there are bras and kets, which represent different dimensions. And so a ket, you have, as you can see, the number of possible states. Bras are a little bit more complicated. We can get into that another time. But for now, I just wanted to cover kets because they're kind of the basic. It's kind of beginner linear algebra. Bras get a lot more complex because it goes into like imaginary numbers and some really weird stuff. But yeah, do you guys have any questions about this or anything? Nope. Okay. So next I got like a nice 8-minute PBS video. If she does a really good job of keeping it entertaining and explaining this stuff. So I'll go ahead and play that right now. Can you guys hear okay?
Yeah.
Okay.
Quantum computers don't exist yet, at least not physically.
This is a little bit of an older video, so they kind of actually do partially physically exist now.
But if we peek into the world of mathematics, where they do exist, we can learn how they might work. Let's break down the mathematics of a quantum computer in 3 parts. First, what is a quantum computer doing? Second, how do we represent it mathematically? And third, why is quantum computing so amazing? Part 1, what is a quantum computer doing? The fundamental unit of a classical computer is a bit. Bits have 2 states, 0 and 1. Computers take in a string of bits. In this example, it's a string of 8 bits, and use logic gates to switch some of the bits, like this. Okay, that's kind of a crude description of a computer, but it works for our purposes. Quantum computers use qubits, a portmanteau of quantum and bit, which is kind of funny because bit is a portmanteau of binary and digit. Anyway, like a bit, a qubit can be in state 0 or state 1. And like a classical computer, the initial program for a quantum computer is just a string of zeros and ones. But While a quantum computer is running, its qubits can also be in infinitely many superpositions.
By the way, if you guys have any questions, feel free to stop. And sorry if this video is a little bit repetitive based on what we're covering, but I think about at the 3-minute mark, she starts getting into some new stuff.
Between 0 and 1. When a qubit is in a superposition, it has some probability of being in state 0 and some probability of being in state 1. You can think of a superposition as being a limbo state, partway between 0 and 1. But superpositions are fragile. If we look at it or try to measure it, the qubit will collapse into a basic state, either 0 or 1. You might know this from the famous Schrodinger's cat thought experiment. Before opening the box, the mythic cat is in a superposition of alive and dead. But when you observe the cat, it is forced to pick a state, alive or dead, not both. A quantum computer is essentially full of Schrodinger's cats. Actually, qubits are not made of cats. Qubit materials are usually things like electrons, where spin up corresponds to state 0 and spin down corresponds to state 1. But I've digressed. That's the realm of physics. Let's see an example of a quantum computation with 2 qubits. There's 4 basic states, 0, 0, 1, 0, 0, 1, and 1, 1. These are the states that 2 classical bits can be in. But there are also infinitely many states formed by superpositions or combinations of these basic states. Each operation of a quantum computation is performed by a quantum gate, which, like a classical gate, changes the state the qubits are in. Let's start our quantum computation in state 0, 0, and then apply a quantum gate. Now, the qubits are in a superposition. There's a 1/2 probability, or 50% chance, of being 0, 1, and a 1/2 probability of being 1, 0.
So real quick, just wanted to point out the ways that this represents the probability density matrix. So when you have 2 bits in the superposition, you see that you have the square root of 1/2 representing both of these Dirac notations. And if you square them and then add them together, based on how many states you have, it equals 1, because 1 represents 100% probability. And that's kind of the math that this relates to then the probability density matrix, which is the probability of these bits collapsing to that certain state. So with the 0, 1, there's a probability of 50% chance that it collapses to the second position. And then with the 1, 0, there's a 50% probability of it collapsing to the third position.
Ignore the square roots, I'll explain them in a minute. The particular superposition it's in is a result of the quantum gate we chose to apply. Here's one more quantum gate, changing the state of our computation. At the end of the quantum computation, we observe or measure the system. But we can't see these delicate superpositions. Remember, a superposition...
Whoops, sorry.
And look at it from the perspective superpositions. Remember.
So yeah, again, just with that probability density matrix, you have square root of 1/2 squared, square root of 1/6 squared, square root of 1/3 squared, 1/2 plus 1/6 plus 1/3 is equal to 1. So you have the 50% in the second position, the 18.3% chance of it collapsing to the third position, and then the 33% chance of it collapsing to the fourth. And you can manipulate this by applying the quantum gates. And of course, I restarted it again. Sorry about that, guys. No worries.
You can't see these delicate superpositions. Remember, a superposition is like a limbo between basic states. When you observe the computation and look at it from the perspective of these basic states, it must pick one, collapsing the wave function and revealing a single basic state. In this case, it collapsed to state 0, 1. If you run the same computation repeatedly, the final result will be 0, 1 half the time, it'll be 1, 0, 1/6 of the time, and 1, 1 1/3 of the time. That's what the numbers in the superposition tell you, the probability that the superposition will collapse into each basic state. So, if you run the computation 100 times, roughly 50 times it'll result in state 0, 1, 17 times it'll result in state 1, 0, and 33 times it'll result in state 1, 1. This allows you to recover the probabilities and therefore the final superposition of the computation. This doesn't seem very efficient with 2 qubits, but as we'll see later, it can save you a lot of time with more qubits. So what's the math behind all this? Part 2, mathematical representation. A vector can be a pretty abstract concept in mathematics, but for our purposes, we'll just say a vector is a list of numbers, and the dimension of that vector is the number of numbers in the list. Here's an important caveat. For now, to help us get through the first part of the explanation, we'll only work with non-negative real numbers. But actual qubits use negative or even complex numbers. But I'll get back to that later. 1 qubit is represented as a 2-dimensional vector. This is state 0, and this is state 1, and this is a superposition. Here's the reason for the square roots. We can visualize the vector on a circle like this. The horizontal component is the square root of the probability of being in state 0, and the vertical component is the square root of the probability of being in state 1. By the Pythagorean theorem, the length of the vector is 1. Each point on the unit circle is a quantum state. A classical computer can only point up or right, but a quantum computer uses much more of the circle. What about 2 qubits? It takes a 4-dimensional vector to represent the 4 possible states. Here's the earlier computation in vector form. The formula for the length of a 2-dimensional vector easily generalizes to the formula for the length of a 4-dimensional vector. So, as we said before, all the quantum state vectors have length 1. The 2-dimensional vectors pointed to a spot on the unit circle in 2-dimensional space, and these 4-dimensional vectors point to a spot on the unit sphere in 4-dimensional space, which makes it awfully hard to visualize. If you have n qubits, there are 2 to the n basic states. So the quantum state is represented by a vector on a sphere in 2 to the n dimensional space. Quantum gates change the system's state. So they move the state vector around the sphere. Mathematically, this is represented with a unitary matrix. Don't worry if you haven't learned about matrices. For our purpose, a matrix, specifically a unitary matrix, is a block of numbers that describes how vectors move around the sphere. When we multiply it by the starting vector, 1, 0, 0, 0, we get back a new vector, which represents our second state. Each quantum gate is a different unitary matrix, changing the vector, which represents the state of the qubits. Okay, here comes the caveat I mentioned earlier. We just applied this quantum gate to the state 0, 0, represented by this vector, and got this state as a result. But if we apply the same gate to state 1, 0, represented by this vector, we get this state as a result. What's funny about that? This superposition has negative numbers in it, and that's totally okay. To get the probability that the qubit collapses into each basic state, we just take the absolute value of the numbers. In fact, not only can these numbers be negative, they can actually be complex numbers. So if complex numbers are familiar to you, notice that the state of n qubits is actually represented on a sphere in 2 to the n complex dimensions, which has twice the dimensionality of the sphere in 2 to the n real dimensions. If you're not familiar with complex numbers, don't worry. It's not necessary for this video. Okay, aside over. But what's the value of all this quantum computing?
So go ahead and stop there. You guys hear me okay?
Yeah.
All right,
Yeah,
cool. Sorry, just had to plug in my headphones again. So yeah, if you guys want the link to the rest of this video, we can stop there. It about covers the mathematics of it. So yeah, I really like the block sphere representation of it. Ones and zeros are very discrete. When you start picturing things on a sphere, though, it can kind of make sense. You have this multiple dimensionality aspects of these qubits, and these are represented by Dirac notation and these matrices. Next week, get a little bit more into quantum gates. They kind of gave a random quantum gate there. Didn't really explain it a lot, but those quantum gates are like pretty interesting and cool. They're the avenues of which how we manipulate the quantum states so that we can perform some cool computation on it. And I know it probably is hard to see when there's only a small number of qubits, but when you get to larger number of qubits, they can really start to speed up stuff like search algorithms, which if you familiar with quantum computing, it's like, how do you find the specific value that you're looking for? These quantum gates can really speed up search algorithms and stuff like that in order to more fastly compute things, which would benefit a lot of things. But yeah, we can get a little bit more into that next week. But and then also here, so we I think I gave an example. Here's the Hadamard gates, and this is how we get things into superposition. And here we are tensoring. When you tensor two qubits together, that's how you combine two single qubit states. When you tensor them together, that's how you can create this chain of qubits that then exponentially increases the number of states you have. So you have Dirac 0 and Dirac 1, and then, or Ket 0, Ket 1. And when you tensor them together, these qubits only had two possible states, but now you have four possible states. And if you added a third qubit, now you would have eight possible states. And when we perform the Hadamard matrix on it, which is this unitary matrix right here, which is the 1, 1, 1, -1 matrix down at the bottom, when you tensor that, when you add that into the equation, then you start to have these qubits in superposition, which means that they don't represent a single possible state. They represent probabilities of all the possible states. So on the top, you have qubits tensored together, but they're still just in one of those four possible states, just because of the values that they were before. But then when you add the Hadamard matrix in the mix, that's when you start to get qubits in superposition. And then that's when you can start doing fancy stuff and performing some cool computation, taking advantage of that superposition to speed things up. So the takeaways would be tensors. You can combine these qubits together. The kets are just a way of mathematically denoting these vectors. The way that you can translate these kets and these vectors into the probability of density matrix via the equation of squaring all the numbers, and then they should equal to 1, and thinking of this as kind of a sphere, and where the qubits represent different points on the sphere, and how that there can be complex numbers in the mix here, which just adds more dimensionality, which then gives you more possibility of superposition, cancellation, and stuff like that. So yeah, I think that's about it. Any questions?
Not from me. I thought that was really helpful. I really liked the video. There's a lot of things that in the next talk that I'll start in the next couple of minutes are directly applicable. And so I think this was awesome. This was super cool.
Well, thanks. So yeah, here's some resources. I think so these are supplementary. This top video it's an hour and a half, so it's long, but it's this guy from Microsoft Research. He's super personable. He like really takes the time. I think what his talk was, he was doing a presentation at Microsoft to a bunch of people who also work at Microsoft who didn't know how quantum computers worked. So he describes it at a very low level and then builds up. And it's an hour and a half, but honestly, he does a really good job of keeping it interesting, kind of like those people. Maybe not quite as graphic-y and smooth like those PBS videos, but pretty smooth. And he treats everything very simply and describes everything pretty well. And then the second video right here is a Shor's algorithm video, which takes advantage of those quantum gates and those quantum positions and superposition, probability density matrix, and it actually does something useful. And for anyone who knows, Shor's algorithm is the one that can break encryption. So if you've ever heard anyone say that like Bitcoin, a quantum computer breaks Bitcoin or breaks cybersecurity, that is the algorithm that does it. And it's one of the like leading algorithms that is like, it's one of the leading applications of quantum computing right now. Like in the foreground, something that is almost like a direct threat and a direct application versus some other stuff like quantum chemistry. Machine learning is a little bit more abstract, a little bit more complicated, a little bit further down the line. But Shor's algorithm could be something that could be applied in the near future to really change up the game of cybersecurity and just encryption as a whole. So yeah, I think that's all I had. Any questions? Cool. Okay, I'll let Teddy take it away.